every single grade. And that's the story of the evolution of Wade.
Now for a horizontal distance problem, how do we know that these are aligned horizontally? Oh, they have the same y-coordinate, don't they? Right 1 up 5, and then right 13 up 5. They're both 5 feet above sea level, if you will. So it's perfectly horizontal, straight across. Horizontal distance. When your brain looks at 1, 5 and 13, 5, you probably think 12. And that would be correct. Horizontal distance is 12, but how does your brain do that so fast? Because your brain is actually thinking 13 minus 1 is 12. Or maybe even you're doing the add back method that I taught you back in Integrated 3. Your brain is thinking 1 plus how many steps does it take to get to 13? So here's the actual way to do a horizontal distance. It's really the right x, the larger x, minus the left x, or the smaller x. And you ignore the y's because they're the same. So we'll put right x minus left x. And you want to keep that in mind for the whole chapter when it gets way more abstract and you can't tangibly look at that and think 13 minus 1. When it gets a little crazier, just everybody revert back to this and you will completely understand how to do the harder problems. So now for part A, we've got a vertical distance. Within the curve, x equals y squared. Okay, we've taken away the numbers now, so we've got to think more abstract, but with the same rules. So first of all, if you've been in my classes, we've graphed a lot of y equals x squared. We haven't graphed very many x equals y squared examples. So if the squared is on the y and not the x, this is a sideways parabola, okay? It's not y equals square root of x, but it's similar. Y equals square root of x is only the top half. If it's still x equals y squared, it is the entire, plus or minus, by the way, top and bottom. So when you see this, I want you to think origin and then sideways parabola. Hey, how do you survive in calculus? Thou shalt know thy graphs. That's what we always say, right? So here we go, sideways parabola. Now, what is the vertical distance from any point on the top of the curve straight down to any point on the bottom of the curve? This is the kind of stuff you'll have to do in this chapter. All right, well, let's see. Vertical distance. Isn't vertical distance top y minus bottom y? Okay, so what we need to do is take the top y coordinate, but we don't have a specific coordinate, minus the bottom y coordinate. Okay. Well, let's see, what's the top y? Y equals what? Well, you see this equation's not solved for y. So what we need to do is we need to get y by itself. If it's by itself, you're good. If it's not by itself, you have to get it by itself, okay? So the y coordinate shall equal, take the square root of both sides, but then when you take the square root of both sides in math, don't you create your own plus or minus? Wouldn't y be equal to plus or minus square root? Hey, guess what? The positive square root is the upper half, and the negative square root is the lower half. It's two different equations put together, all right? A positive square root of x, and then its y-axis reflection, negative square root of x. So the top half is y equals positive square root. The bottom half is y equals negative square root. So you would have to do that a couple of times in this chapter when y is not by itself. Don't worry, often y is by itself. Okay, now, what's the top y coordinate? I don't know, I don't have a y coordinate. But you know what? The y coordinate is the square root of the x coordinate. The top y is whatever the square root of x is. And then of course you would be provided a specific x in some cases. Sometimes it's just more general. Minus, what's the bottom y? All the bottom y coordinates here, they are the negative square root of the same x coordinate. So the bottom y is negative square root of x. So over there we subtracted numbers, now we're subtracting actual equations, expressions, because we're trying to write just a general formula for how thick is this no matter where you go. Can you imagine engineering problems, by the way? A lot of engineering problems caring about how thick something is, right? Architecture problems, right? Considering how thick something is to support the weight of like a bridge or a building, okay? Very important. So, top y minus bottom y is actually square root of x minus minus square root of x. Minus minus becomes a plus.
And your formula is square root of x plus square root of x makes 2 square root of x. There is the vertical distance at any possible x coordinate. And all you did was top y minus bottom y as an equation, not a number. Okay? I could come through here and say, hey, engineer, if I go way out to 144 meters, inches, centimeters, miles, whatever this is, if I go out to 144, how far apart are these two curves? Maybe they're roads. Maybe this is a road engineer. Take 144, you could plug it into the equation, get the square root of 144 is 12 times 2 is 24, whatever the units are. Okay, so you could figure out thickness 24 or wherever they want to specify, whatever x coordinate they want to specify. Okay, so that's how this stuff is used. All right, so now that you've seen that one, now let's try another spin-off of that. Now I find that students who have gone through a traditional system of Algebra 1, Geometry, Algebra 2 really get to study this shape, whereas the integrated program, if you've gone through integrated math 1, 2, and 3, doesn't really cover this shape well. It doesn't do it justice. It doesn't cover it at all, as a matter of fact, which is not good. So I'm going to try to fix that right now. Okay, do you remember something like this earlier in the year in calculus? Do you remember x squared plus y squared equals 100 was the equation of a circle with a radius, because 100 is r squared, that's a radius 10. All right, if you remember that, that is the equation of a circle. And this looks like it, but here's the thing. What are the coefficients of x squared and y squared? Isn't that 1x squared and 1y squared? The coefficients are the same. By the way, if you made this 9 and 9, it's still a circle. We never see that form, but it is still a circle. If you just divide each term by 9, you would now have x squared plus y squared equals 100 over 9. That's still a circle, okay? If the coefficients are the same. These coefficients are not the same. I wonder what this shape is. It's an altered circle. Well, what's an altered circle? An ellipse. It's elliptical. It's either been stretched this way, long ways, or it's been stretched vertically. So, here's the question. How do I know this graph if I've gone through the integrated system and not Algebra 1, Geometry, Algebra 2? How do I know that this is an ellipse? Because the coefficients are different, right? And because it's x squared and y squared both, which encloses the shape like a circle or ellipse. Second, how do I graph it quickly, Mr. Wade? Tell me how to graph it. Show me the secrets. Okay. If you plug in x equals 0 temporarily, you can get the y-intercepts. All right? Now we'll give you the y-intercepts. If x equals 0 in any problem at any level of math, that will produce y-intercepts. 9y squared equals 4. Divide both sides by 9. Y squared equals 4/9. Take the square root of both sides. Y equals plus or minus, square root of 4 is 2, square root of 9 is 3, plus or minus 2/3. Now also, how do we get the x-intercepts? If you plug in y equals 0 to any equation in math, you can get the x-intercepts. So that would be x squared plus nothing equals 4. Aha, the x-intercepts are plus or minus 2. So it's just as simple as quickly getting the x and y intercepts, and now we can draw that as a graph. All right, so let's try it. So it hits the y-axis at plus and minus 2/3. Let's call this 2/3 here, and we'll call this negative 2/3. Okay, you don't have to draw it to scale, but it's kind of nice to do so. If that's only 2/3, then 2 is going to be a lot more, isn't it, right? 2 is going to be more like this, but it's an x-intercept. So let's put 2 like way out here, and let's put negative 2 like way back here. Plus or minus 2, those are your x-intercepts, and you can see that this ellipse has been stretched long ways, like this. All right, and there is your ellipse. Had you taken pre-calculus from Mr. Wade, I would have taught you this, and I would have taught you that this is called an oblate ellipse, as opposed to a prolate ellipse. But that's if you took me for pre-calculus. The point is, you now know how to graph it quickly. So find the vertical distance of this oblate ellipse. Straight up and down, vertical distance. Okay,
the vertical distance from any point on the top to any point on the bottom would be top y minus bottom y. Isn't that vertical distance, right? So v equals top y minus bottom y. It's our new formula, right? But not with numbers, with variables this time. Okay, I need to find the top y equals and the bottom y equals so I can figure out the formula. Well, I don't have y by itself, but I could get it by itself, couldn't I? Let's resolve this equation for y here. So let's see. Let's do this on the other board because I'm running out of space. How to resolve an ellipse for y. Well, first of all, let's subtract the x squared over to the other side because that has nothing to do with y. So 9y squared equals 4 minus x squared. All right, divide both sides by 9. So we're just going to move that underneath this thing right here. And then take the square root of both sides. And of course, that's where you put in the plus or minus, right? Y equals plus or minus. Now, when you take the square root of a fraction, you take the square root of the top and the square root of the bottom. The square root of 4 minus x squared is simply the square root of 4 minus x squared. Don't you dare distribute a radical across an addition or subtraction and tell me that that's 2 minus x, because I see students do it all the time, and it gives me a heart attack. We don't need that. Now the square root of 9, you do know is 3, so go ahead and release that one. You don't need a 9 under a radical, okay? So I think that goes back to our pledge, basically. So take the square root of the perfect square. Do not distribute the square root across subtraction. Now, wait a minute, plus and minus, there's a reason it's plus or minus. Isn't plus the upper half of the ellipse, and the minus is the lower half of the ellipse? So let's go back over here, and we're going to call the top half positive square root of 4 minus x squared over 3. And the bottom half negative square root of 4 minus x squared over 3. And this is the kind of stuff you'll be doing in this chapter. All right, very important to be able to solve for y, and sometimes we'll be solving for x. That'll come later. So, the vertical distance from any point from the top to the bottom. By the way, this could be a track, like a track that people walk around that you're trying to design. This could be the base of like a football arena, like one of those indoor stadiums. This could be a lot of things in real life, and it is a lot of things in real life. Okay, so this is very important, right? Vertical distance is top y, square root of 4 minus x squared over 3, minus the bottom y, negative square root of 4 minus x squared over 3. And minus minus makes a plus, and it already has a common denominator for you. So essentially, you get the square root plus another square root makes 2 square roots of 4 minus x squared over the common denominator 3. Or as Mr. Wade prefers, I like the 2/3 on the side. So the best vertical distance, and you'll see why this is an advantage later on, by the way. There's a reason I teach you all this stuff. There's a method to the madness. I don't teach you stuff that's not going to factor in later, okay? The 2/3 on the side is going to help you a lot in this chapter. Organize your work better. Not that this is wrong, but this is going to be better, you'll see. All right, so that's how you do one of those with an ellipse. We'll have some ellipses in this chapter for sure. Okay, now let's try another problem. So now we've got 2x plus 3y equals 12, okay? What kind of equation is that? Know your equations, know your graphs, know your pictures, right? That's a line. 2x plus 3y equals 12. It's really y equals mx plus b if you were to resolve for the y. So I do want you to recognize x to the first, y to the first, linear. Okay? If you ever had a teacher that taught you standard form, this is called standard form of a line. It's called ax plus by equals c. Maybe they taught you that, maybe they didn't. But that's just a harmless line, okay? I just realized, this really isn't a calculus lesson today. I'm teaching you all the algebra that you probably never learned just to be able to do calculus. So today is just pure algebra, no calculus at all. All right, boy, we sure are kind of scraping the edge of calculus in this question, though. Let me tell you, we're really warming up for the rest of the chapter here. So how do I quickly graph 2x plus 3y equals 12 if I know it's a line, but I'm not quite sure how to draw it? Same thing as last time, just like the ellipse. Give me the x-intercept, give me the y-intercept, and you can graph just about anything, all right? So x equals 0. We'll hide the 2x, right? It's kind of like the old hiding game, and you get
3y equals 12, so y equals 4. It's hitting the y-axis at 4. Okay, by the way, you also will be using the x and y intercepts in the calculus part of this chapter. So actually it doesn't just help you graph, it gives you numbers that you actually need, as you'll see. Y equals 0 will give us the x-intercept of any equation in any level of math. So if you put in 0 for y, you get 2x equals 12. Well, guess what? Divide by 2, x equals 6. X-intercept, y-intercept, easy, and it's a line. So let's draw a graph, the coordinate axes, and we've got 6 on the x-axis, 4 on the y-axis. Let me try to make my 4 a little bit lower than the 6 is wide, but again, doesn't have to be perfect. Okay, try to make it somewhat to scale. It's a straight line, and it is a negatively sloped line. I didn't see any negatives in the equation. I bet when I get y by itself, though, I bet there's going to be a negative slope. You betcha there is, all right? M is always in front of x if y is by itself. Okay, now, here's what we're going to do. We're going to find the area of the circle. Wait, circle, where's the circle? Around the x-axis. We have a little bit of new lingo in the explanation of this. It does say, I didn't put it on the board, but it does say there's a region that's enclosed by the line and the coordinate axes. Now, axes is the plural of axis. So the region enclosed by the line and both axes would be y-axis, x-axis, line. The only region that is enclosed by all three of those figures at the same time, y-axis, x-axis, line, is a triangle. It's a right triangle. Okay? So that's another thing we're going to be doing in this chapter. We're going to be enclosing regions by boundaries. All right? So there's your shape right there. We're making shapes now. Okay. Now, pick a point on the line, and it says that we're going to take a point on the line and we're going to rotate it around the x-axis. I don't know, in all your years of schooling, all the stuff you've ever learned about mathematics, this could be the first time in your life that you've actually come off the board or off your paper, okay? Three-dimensionally. This is a big moment. Once again, I'm going to take this point, and then imagine that the x-axis is, let's put a dashed line. I know that also means asymptote, but in calculus it also means axis of rotation is what we call this. So imagine that this is this invisible axis right here. And this point is going to orbit, just like a planet around the sun. This point is going to leave the board and make a circular path around and then back through the wall and then back to that point. Okay? It's hard to draw, of course, three-dimensionally, but we can kind of do this. All right? So it's going to come off the board and behind the board and make a circle. All right. Find the area of that circle. What in the world are we doing now, right? So it turns out that a major theme in this chapter is building shapes by building a bunch of circles or stacking a bunch of circles together. So this is going to be a very key thing. So imagine the circle coming off the board and then behind it. Imagine that from the axis of rotation to the point on the line, that's the radius. Okay, that's your radius of the circle. And we're coming out three-dimensionally. So the first thing I would write down is the area of a circle from those old classes is, of course, pi r squared. That's a thing on the ACT that nobody's supposed to miss. So that's easy. Check this out. The radius. The radius is a real-life vertical distance. How about that? Now see, the vertical distance is coming in already. So the radius is going to be top y minus bottom y. And that's a lot of what you'll be doing in this chapter, and then quantity squared. So, what's the top y? The top y, for this point right here, is, well, we don't know what that point is, do we? We don't know what the top y coordinate is. But it's whatever the line allows it to be, right? Which would be this equation, but wouldn't we have to resolve for y? So let's subtract the 2x over. So 3y equals 12 minus 2x. Now divide everything by 3. And it turns out, now probably in those older classes like integrated 1, maybe sometimes integrated 2, you probably put like the 12 over a 3 and the 2x over a 3, like each individual one. Turns out in calculus, it's actually better to just keep it quantity over 3. That's going to be way better for this chapter. So just start doing that in calculus, okay? There are some minor differences, of course, between calculus and the old integrated classes. So that is the equation of the line written in a different way, all right? The top y is whatever 12 minus 2 times x coordinate over 3 allows it to be. So you get pi times 12 minus 2x over 3 minus, now the bottom y. The bottom point is sitting on the x-axis because this is going to be the rotation. I just happen to draw the circle here, but the circle could be over here. Couldn't it be a little circle like that? Couldn't it be right here and be a big circle at the 4? So we don't know where it is. We're trying to write just a generic formula for all of it. Wherever you are, the top y is definitely on the line, and the bottom y is definitely on the x-axis. If you are on the x-axis, isn't your y-coordinate 0? So your bottom y is 0 for the first time today, okay? So of course we can just drop the 0, and we can go ahead and square this fraction. So pi, all right, 12 minus 2x squared is simply 12 minus 2x quantity squared. Don't you distribute a power across subtraction or addition, right? But when you square the bottom, you can square the 3 and make it into a 9, okay? Now, of course, this is fine, but you know what Mr. Wade prefers, right? Pi over 9 on the side will make your life a lot easier in this chapter. That is the generic equation for any circle rotating around an axis, the x-axis specifically, at any point under this line. All the possible circles that are rotating around this axis. If you think this connects to like planetary orbit, you're darn right it does, for sure, all right? The study of outer space, yes. So this thing right here will basically give you the area of that circle for any x value. We could even test it out, okay? We could test this out. Let's just pick a random x coordinate. How about 6? Okay, let's just go over to 6. All right, if I pick x equals 6, just to make sure this formula is legitimate, all right? Are you legit? Well, let's find out. So the area of the circle at x equals 6 would be pi over 9 times 12 minus 6 times 2 is 12, quantity squared. Well, 12 minus 12 is 0, and 0 squared is 0, and 0 times anything is 0. Wait a minute. Why is the area of my circle 0 at x equals 6? Oh yeah, look at the picture. If you're doing the radius from the line down to the x-axis to make your circle, by the time you get to 6, there is no radius from the x-axis to the x-axis, right? Or from the line to the x-axis. There's no circle. The circle area is 0. That formula does work. How about them apples? Now, problem D is a spin-off of the one we just did, but it's horizontal distance. Okay, we have not done horizontal distance yet today, except for with those original points in the warm-up. Those were actual tangible coordinates, like numbers that you can see. What happens when it gets more abstract? Okay, let's try to stick to the rules. Just be a little bit more general. So, we still have, I've just redrawn it over here, we still have that line, that diagonal line, enclosing a triangular region with the 2 axes and the line. So, we have y solved for from before, but we're going to have to switch up our game a little bit here. Horizontal distance. Well, horizontal distance, remember, is right x minus left x. That's how your brain does horizontal distance, okay? It does it with numbers. Can it do it with equations? Absolutely it can, all right? So we're going to pick a point on the line. It doesn't matter where you pick it. Any point on that line. What is the horizontal distance across this enclosed region? What is the thickness of the triangle at any place? This is not like going back to integrated and saying, oh, the base is 6. Yeah, the base is 6, but we don't care about that. We care about the thickness, which actually varies. It's not always 6. 6 is its biggest. So since the width varies of the whole shape, we have to use a variable, because vary is the root word of variable, right? So let's write a variable formula that tells us the thickness. All right, the right x is on the line, but we have it solved for y. I guess we better resolve this for x, right? What are all the x coordinates on the line? That's something we usually don't do in math, do we? Usually we solve for y. Let's resolve this. Let's do 2x equals subtract the 3y over. Okay, divide both sides by 2.
And again, let's put the whole quantity over 2 because that's going to be a lot better in this chapter. Okay, now there's something we haven't done before, but all you students are good at algebra. And you look at that and go, I can solve for any letter. Give me any letter, Mr. Wade, I can get it by itself. Okay? So, every x coordinate on this line representing this point shall be 12 minus 3 times whatever the y coordinate is over 2. That works. So the right x is 12 minus 3y over 2 minus the left x. It says that it has to go across the shape. Basically, the instructions say you've got to go all the way across the region. So that means the left boundary, no matter where you go, won't it always be on the y-axis because that is a boundary? The left x on the y-axis is always going to be 0, right? Isn't that x equals 0? So your left x is 0, which is very common. It doesn't always happen. But it's very common that you get a minus 0 somewhere in your formulas, okay? Most of the time. Drop the 0, you have a formula. That is the horizontal thickness of this triangle. And boy, will we need that fact to do the other crazy things we're going to do in this chapter. Okay? Very simple. All right, one last problem. Let's do it over here on this board. All right, same shape, same enclosed triangle, but this time we're going to rotate a random point on the line. So let's pick a random point on the line. Okay, you can redraw your triangle if you want to redraw that right now. And we're going to rotate that point around the y-axis. So now the rotation's going like this. All right? And that's kind of like a flattened circle. It's all about perspective, right? Not that I'm a great artist, but okay. So again, it's coming off the board. That's the semicircle to there. Then going behind the board and completing a full circle. So it's orbiting around the y-axis. All right. Find the area of that circle. Here's your radius right here. So the area of that circle by taking a random point on the line, rotating it around the y-axis only in this region. So the area of a circle is again pi r squared. The radius of this particular drawing is a horizontal distance, not a vertical distance. So we get pi, insert horizontal distance right here. Wait a minute, the horizontal distance was the last problem we just did. Insert 12 minus 3y over 2 right there for horizontal distance. All right? And again, this is just an algebra lesson. But calculus teachers who don't take the time to explain this pure algebra lesson will pay the price later when none of their students understand, or most of their students don't understand the calculus. But now you'll have a very firm foundation in Mr. Wade's class. That's how we do it, right? Okay. First of all, to square the fraction, PEMDAS, exponents first, square the top, square the bottom. If you square the top, it's nothing more than 12 minus 3y quantity squared because you can't distribute a squared across a subtraction or addition. How many times have I said that today, right? Okay? Now, if you square the 2 on the bottom, though, you will get a 4. So we'll put it over 4, or even better, could we slide that 1/4 off to the side and put it with the pi? And that is the area of any circle from the little tiny circles up here all the way to the big circles down here that fit in that region. By the way, if anybody thought that maybe the line is actually rotating and making a cone facing down, yes, that is absolutely correct. Okay? Although, now here's a twist. This happens in calculus. We eat ice cream cones like this, right? Turns out in mathematics, though, way back in the BC era, we established this as the standard cone. The standard cone goes like this, what we would think of as upside down. And this is called in calculus the inverted cone. Of course, in the BC era when they discovered cones and all these rotations, this was a long time before ice cream cones were invented, right? So actually the cone came way before the ice cream cone in geometry. So there you go. There's your fun fact of the day. We actually eat out of an inverted cone, and this is a standard cone. There you go. All right. So is that it? That's it. That's all for 5-1. All right. Now that you're all algebra geared up, you can try some of the homework, and then we can get into 5-2, where we're going to start applying this stuff to real life calculus. Let's do this.
Hold it now.
Vertical distance and horizontal distance. We'll call this capital H. Yeah, not 2, but 12. Mr. Wade, you dummy, you idiot. Kind of like up here, where we ignored the x's. Left, right. You stupid idiot, wake up. Square root of 4 is 2. Square root of 3